Welcome back, my statics friends. We've been working with centroids and finding centers of area and centers of mass. And in our last video, we talked about how we could find the centers of force for distributed loads. We're going to continue that thought and move our attention more towards an application problem involving fluid pressures or in static fluid pressures. So I'll show you how to do that in this video. So without further ado, let's get started. So as we start turning our attention to fluid pressure, we're going to basically be doing some basic statics pressure kind of calculations. And so the way that we start to look at this, and this approach will work for even, soil pressures to a certain degree, that they'll all have very similar setups for, rigid body mechanic type applications. Now, there's a lot more to fluid behavior than what I'm getting ready to show you, but if we just want to find, the basic pressure on a static surface underwater, this method will work just fine for that. But if the water is moving or impacting in any certain way, this isn't the approach that you want to do. You'll have to count on doing something with fluid dynamics or something. It would be a later course that you take after this. So we're going to keep it fairly simple in this discussion. All right, so the way that we set these up from a static standpoint is we imagine drawing our water surface, okay, at which we have a pressure that we're going to say is equal to 0. Now, this is, kind of our standard pressure, if you will, as opposed to, say, an atmospheric pressure, because obviously there is pressure in the atmosphere that's pushing down on the water, which causes pressure as well. We're just saying that relative to the water itself, our pressure is going to be equal to 0. And so we're going to define, say, the height of the water or the depth of the water as a dimension z, and it's measured from the water surface down to the point that you're interested in. Okay, and so the pressure at a point at a depth of z is given by the equation P equals gamma times Z, where gamma is something known as the specific weight of the fluid, and it is unique. It's a function of the density as well as gravity of the fluid multiplied by this Z parameter, which was the depth. Okay, and so at Z equals 0, we had 0 pressure. Okay, at half of Z, we have half of what we do at the bottom. Okay, and so it's this linear relationship that exists, or if you look at it from the side, it is a triangular loading that acts in all directions. Now, we're going to assume that the particle that's here, if he wants to push up, that the particle above him is holding him down to some degree. Okay, again, we're making some gross simplifications here, but in the lateral direction at the surface of the wall, this is what the pressure looks like. Okay, so that's the way we're going to kind of handle it. Now, we talked about gamma. Gamma is the specific weight of the fluid. Okay, for water, gamma, and again, we know for water that this changes with temperature, so we're going to be assuming 70 degrees approximately. Okay, that for our typical static calculations, our gamma for water is taken as 62.4 pounds per cubic foot. Okay, and this is an English unit. Okay, and then we're going to take a look at in the metric units or the SI units, it's taken as 9,810 newtons per meter cubed. Okay, so we're going to be building up to some pressures that we're going to start seeing. Okay, that for pressures we're going to have you'll see things like pound per foot squared. You may see that written as PSF. Okay, a newton per meter squared is something known as a Pascal and is abbreviated as a PA. Okay, so you'll see those units kind of tossed around, and sometimes you won't see newton per meter squared. You'll see a Pascal as the value there. Okay, so to kind of summarize, then we're calculating pressure at a whole lot of points, from 0 all the way down to our depth Z. Okay, and that's gamma times Z, and then gamma is rho times G, which this is the density, and that's gravity, and that's the depth. Okay, and that's the way that we'll start to kind of build our pressure. Okay, once you have that, if I take this problem and I turn it this way, this starts to look a whole lot like those triangle problems we solved in the last video, talking about centers of forces and stuff. And in fact, the methodology is exactly the same. Now there is a couple of things that we got to kind of look at, but let's start with just the basics. Let's take our idea of forces and finding equivalent, single resultant forces and their location and draw the picture this way. So if I want to find the force that's acting on the wall of this, I would have, here's my triangular pressure distribution. And again, I like to draw that as a dotted line, just so kind of as a reminder of the original shape. Okay, and then this whole area gets resulted and turned into a single resultant force that is acting at the centroid of the area. That's exactly what we did with the forces in the last video. Okay, so if the depth of the water is z, then this force is located at 1/3 from the high end, or in this case, z over 3 from the base, or from the bottom of the loading point. Okay, and again, the bottom point here is actually a value of gamma times z. Now, one thing that we need to kind of look at, if we kind of start to calculate this a little bit, is if we do our area calculation on this before, I get a 1/2, which area of triangle is 1/2 base times height. The base is gamma z, and the height is z, and 1/2 of that value will give me the term that you see here, this 1/2 gamma z times z. Now, one thing that we have to kind of watch on this is we have to watch our units, because here's what's happening. On our force, so if we calculate our force resultant as 1/2 gamma z squared on this, all right, gamma we know is, if we kind of look at our units, we know that we want, let's just do it in the kips or the pounds category. So we'll do pounds over here. I have a pound per cubic foot here, okay, and then I have a foot for z, and I have 2 of those. Okay, now if you look at what happens here, we have pounds on this side that we want, because that's what I need in order to be able to do statics on it, and now I'm left with pounds per foot here. Okay, there's a problem. Those units do not match those units, right? So what we want to look at doing is kind of figuring out, well, what can I do? Okay, now here's where we have to kind of take our diagram and look at it a little bit differently. So we had, if I redraw that a little bit, and I orient it this way, and we draw our pressure profile, it looks something kind of like this. Now there's our triangle pressure profile happening on this, and we just said that we had an FR load happening here. Okay, and then of course this depth we said was z over 3. What we're going to do is we're going to start thinking about this in 3 dimensions, and that's the thing you have to do with fluid pressure problems, is you have to think about them in 3 dimensions. Let's take and let's now turn it this way. Okay, and if I look, if I go back clear and we'll get our wall kind of laid in here, and here's our wall, and then on this back face you would also have a pressure profile that looks something like the following. Right, you would have a pressure profile of a triangle at this one, and at every point in between, and then this is something kind of like that, and every point in between all has the same pressure profile, where this point is gamma times z. So what we do is we can kind of draw this, and now instead of being just a triangle, okay, and every one of these guys has an FR value. Okay, and this guy gets an FR, and so every point, so what's really happening on a 3-dimensional wall of, say, length L on this, let's call that as some L dimension on this, is that we end up building basically a distributed force that acts along the wall at a height of z over 3 that has a magnitude of FR. And if I do it this way, now my units work, because a distributed force, if you remember, needs to be in pounds per foot. Okay, and that's what this guy is. Okay, so now I know that if I take that and I find the area of this distributed load and I multiply it by L, then I have the magnitude of the entire resultant force on this thing. So if I kind of draw this, what you're really doing in this problem is we're taking our kind of our triangular prism here, if you will, and I can do this, 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 and this, and here are all my dimensions. And again, just kind of drawing this so we can kind of see everything. Okay, I can turn this whole thing into a true F resultant, okay, such that FR is going to be equal to 1/2 of gamma times z. That's the area of one triangle. And if this is a prismatic prism, if you will, and then all I have to do is multiply that by the length, and I 1/2, oops, I missed a z. There should be a z squared on this guy, right? Because it's z this way, and it is gamma z that way. Okay, so z and gamma z, and then I take, and now whatever my length is we would now multiply that by some L value. Now, what if you don't know that dimension? You still want to be able to work these fluid problems. So often what we do is we assume what we call as a unit length, okay, for L on this guy, meaning that we're going to assume that he is 1 foot or 1 meter wide. Okay, and so whatever I calculate as an FR value using the formula that I had before has kind of this implied single 1 foot or 1 meter dimension in hiding in the equation. And then we just say that this force, if I assume a unit width, is it kind of what would be then this many pounds per foot of width. And then now the units will match and the units will start to work out for us. So that's kind of one of the tricks that happens on this. We got to be kind of careful of. So you're going to see a lot of calculations now. A lot of textbooks don't show the L. They just show that the 1 is implied, or they just write that formula and say, there's your force. Okay, but inside of that is the assumption that of a unit length that's hiding as this 1 foot or 1 meter, right? So that's kind of where we're coming from and what we're doing. So what we're doing is we're basically saying then, to make the notes thorough, L is equal to a foot or 1 meter. Okay, and that's what you were seeing in the equation that was happening on our original derivation. So it's 1/2 gamma z times 1 foot. And now if you do that, all the units work out because this is pounds per cubic foot, a foot, and another foot. Everything works out to get me pounds here. So we'll basically be doing calculations on this unit width kind of thing. All right. So now if you know that you have the value for 1 foot of width, if the wall is 10 foot long, all I do is I take this value and I multiply it by 10. Or if it's a mile long, I multiply it by 5,280 feet, whatever the case may be. I take this value. So this unit calculation is very, very handy for what we're trying to do. Everything else is done exactly the same way. Okay, I could come in and say, well, this is my wall. It's fixed at the bottom, and so maybe there's a moment, and maybe there's some horizontal shear and a vertical, and I have the ability to go in, and with this load acting on this wall, I could tell you what the support reactions are. What does the shear, that's this guy, the horizontal, what's the normal, and then what's the applied moment that has to happen on that as well. Okay, so that's the case, and we're back to doing exactly what we did in the last video with forces, finding centroids of forces, and then using that to find support reactions and those kind of things. All right, now there are a couple other scenarios that pop up that we do want to take notice of. Okay, the first one is that we want to be looking at the say maybe I have a wall. Most of the time these walls that are built they serve some purpose. If it's a swimming pool, it may be a solid wall, but if it's a dam, maybe they're using that as a power generation source, that they're backing the water up over the to some certain depth, and then they have these gates that they open and close to let certain amounts of water pressure and water volumes come through that then turn some sort of turbine down here that it now generates power off of those. That's a very common construction technique. Well, if you're the engineer that's responsible for designing the gate, you need to know how to be able to tackle how do I find the forces of this gate, and it's very, very easy, really. Okay, all we do is we draw our picture, and here's our gate, and we're going to say that from the water to the top of the opening, if you will, or the bottom of that first wall segment is a depth of ZA, which means then that that this guy is gamma times ZA. That's the pressure. Okay, and likewise, to the bottom of the opening, okay, or the top of the lower wall, we're going to say that this pressure is gamma times ZB. Okay, and if we look, then we still have our triangular pattern. Okay, so this would be, gamma times Z at the bottom for the total depth of the wall, if I needed to worry about it. Okay, but this is what we do. And so all we do then is, if I want to be designing the gate, I can draw a free body diagram of the gate. Maybe it's got 2 bolts or some sort of latch or something that's holding that force in place. If I cut the bolt, okay, what will happen is you get a free body diagram that looks something kind of like this. Here's my gate. There's an axial force in that bottom bolt. There's an axial force in the top bolt. And then all of the pressure that's inside this trapezoidal region, or what's sliding horizontally on this, all of this will impact that plate. The wall doesn't stop and it wants to come through. And so then what we do is we get a diagram that looks like this. Okay, at the top of the gate, I would have a pressure of gamma ZA. Okay, that was what we had here. Okay, and then at the bottom we have gamma ZB. That's what we had at the bottom. And so that now becomes my free body diagram for designing the gate. Okay, and so I can come in and I can say, well, this guy I should be able to calculate. We can split it into, a rectangle and a triangle. We've done that one a couple of times now in our class. Okay, so you should be able to handle that. Okay, we would have to figure out where the centroid is, the centroid of the trapezoid. And again, you could do it as the trapezoid as a single unit, or I can split it into triangles and do two separate resultants. Either way will get you the same values. Okay, and so I would turn that into my equivalent force from the trapezoid, and then I have a tension in the top bolt and a tension in the bottom bolt. This guy you'll know, right? Because you know the dimensions of the opening and you know how deep the water is and you know the gamma of the water. You will be able to calculate this. And so all I have to do then to solve this is if I sum moments at T bottom, I can solve for T top. Okay, and then I can do a sum of forces in the X direction where, because this is an equilibrium where the tension in this bolt plus the tension in this bolt better be equal to the force pushing on it. Okay, and so that's the approach to the way that you start to kind of handle these gate problems. Okay, it's just kind of imagine, here's my force of this trapezoid, and then it's, going to slide over and hit whatever that I want it to be studying for those calculation. So it's pretty easy to do. We can get our resultant force itself. This resultant force then is going to end up being the area of this trapezoid, which is 1/2 of gamma ZB, plus gamma ZA, all multiplied by the height. Well, the height, if it's ZA to the top and ZB to the bottom, then this height right here is ZB minus ZA. Okay, and so you can see that the equation that comes out for the resultant force is 1/2 gamma ZA plus gamma ZB multiplied by that ZB minus ZA multiplied, and I know I kind of ran out of room, you can kind of see it here, multiplied by 1 foot. There's that unit width that comes in. You still got to get him in there because this is on a per foot basis that we're doing all of these calculations. Okay, so I hope that makes sense to you. It's like I say, it's not too bad. You just got to remember the triangle and finding the areas, but then you can use all of the rules that you've been using up to this date to be able to solve for things, that you might not be able to do otherwise. Okay, and so these are some very simple basic statics types problems for fluid mechanics. All right, now there is one other one that we want to kind of talk about, and that is for what would be called as a gravity dam. I've got it kind of drawn here in red. I'll kind of clean this up for us a little bit so we can see things a little better. Okay, that now, what if, one of the problems that you have with some of these walls is that if you notice, if we assume that it's a cantilever, this is a very thin wall that there's you would have to have a very strong connection in the bottom where this thing is embedded into bedrock or it's being restrained to keep this wall in place. That's one of the challenges. But one of the design ways that we handle this is to do something called gravity walls, okay, or gravity dams, where we pour, say something out of, say, concrete or, even earth or soil to some degree can be used. And we know that that's going to be located at some centroid location. Okay, and we're going to say that we know that this is, some distance that we'll call as XC. For the sake of argument, I'm going to set my reference at this wall. You don't have to, but you can put it wherever you want. Okay. So here's my X positive, there's my Y positive, there's my centroid of this wall. Okay, and if we assume that the profile is, say a linear edge, then what happens is you still get our triangular wall load just the way we had before, and it has a horizontal resultant force. And again, we know that, assuming that the water pressure is here, then this becomes my Z dimension. Right? And then the pressure that's here then becomes my gamma of my fluid multiplied by Z. That part doesn't change. Okay, but what does change is because of the nature of this wall, okay, and again, I'm looking at a solid wall, so I'm going to shade that as a solid value. Okay, this wall has a weight associated with it, or this dam has a weight associated with it, and it is located at the centroid of this mass. Again, assuming everything is distributed evenly, all those assumptions we made back on day one of our centroids, okay, that there will be a weight associated with this point, and again, this is on a per foot basis, and it's located at some centroid location. So we can come in and I can call this as Y sub C, and then X sub C would be the distance off of my reference that locates that point C. Okay, the other piece that we have then is another load component, though, that because of the nature of the slope of this thing, there is a load that acts directly over that surface, okay? And it's basically, there is a weight of this piece of the wall water, the piece of the water acting on the wall that we call as W sub W, okay? And it's located, depending on the height of this thing, and the dimensions of this, that there is some, let's just call it as some XW value, on where it's located, relative to, say, this point. And again, this is being measured to the edge of the water, but that volume of water goes from the water surface to wherever it impacts the wall and then continues down as a vertical line to whatever it impacts on your particular structure. Okay, so once I have that, now you've got a free body diagram that involves a weight of water. Well, the weight of the water is just simply the gamma of the water multiplied by the volume of the water that's associated with it. Okay, so if you know these dimensions, so say it's, all the way up to the top of the dam, the height is Z, and then you could, based on the slope of this, you could know the horizontal dimension of this thing. Okay, and so that's 1/2 the height times the horizontal, just like kind of what you were doing over here, but now you're doing it for the volume of water itself. Okay, and then on a per unit basis, we would imply a 1 foot happening into the page. Now, one of the things that you have to kind of watch out for, and one of the things that happens in a lot of our Beer and Johnson sample problems, and even to some degree in design, is that as you're designing your dam, especially if it's a water control problem, then this depth may vary. Okay, at one point in the season, it may be all the way up at the top, and then during the dry season, or when farmers start pulling water out to water their crops, it may move down. And so this Z, you have to be able to handle all of the Z's that come out of this, a Z1, Z2, let's call this, Z full. Okay, it starts to look kind of like that. But in all of these cases, for the first pressure, it was doing, it would be a pressure that looks something kind of like this, and you would solve it exactly the same way. The pressure looks like that. Okay, but then if I come down and I look at the little guy, his pressure is only that size. And so the depth of the water at that point puts a whole lot less pressure than it does when it's very full. Okay, and so that's one of the things that we also have to kind of look at. Now, one thing that you'll notice is that this pressure, we're still drawing our pressures as triangles based on a vertical line. What's really happening, okay, is that if my water surface is here, and I know that's my 0, this pressure actually looks something more like this. Okay, and so we have that dimension, I have this dimension, I have that dimension, and so forth and so on. But our pressure looks more something like this. But what we do is we take this, and because of our principle of transmissibility and forces that can slide on their own line of action, I turn it into this guy. Okay, because the pressures are exactly the same, and I like to kind of stack them this way, where this is gamma Z, and this guy was gamma Z. Okay, so I hope that makes sense to you, that we're just kind of taking things and kind of sliding them around because we're taking advantage of our transmissibility principle. Okay, and that's the way that we start to kind of analyze this particular problem, because the depth is still this, and the top is still 0, and that's the same as that triangle. Okay, so that's why we can come in and we can actually find the area of this by taking the base times the height and then multiplied by 1/2. All that starts to work. So those are some of the things that we have to kind of consider. So you do have to get this extra chunk that's in here. Okay, so for a linear sloped front wall, it's pretty easy to locate where that is. Now the weight of the water, would be at the centroid of the block. For a triangle, this would be 1/3 of that dimension this way. Okay, but there are some problems out there that maybe it's not a triangle, but maybe instead it's some sort of parabola. Okay, well, the approach still works exactly the same. Okay, I come in, here's my water elevation. Okay, my pressure then does this associated with it, and then we do have this sliver of a weight that results in some weight of water here, and then that has some dimension, if I want to call that as x bar W, would be a way to do it. And then once you have that point located, again, that's a C, and you still have your weight of your dam, which is located at its C location. Here's my weight of my dam. Okay, and so it's the exact same approach to what you've been doing up to this point. We're just adding pieces for, based on the logic of what we're trying to do. So there's my force resultant, and now you're off to playing the exact same game for these pressures on inclines or non-vertical surfaces. If your surface is perfectly vertical, you're back to playing with this problem. Okay, and notice there's no weight of the water in here because there's no weight of the water sitting over the top of the dam. The wall is vertical and that's parallel to gravity. But the moment you take it and incline it this way, you have to account for this little extra tidbit that will start to show up there. So I hope that's made sense to you. It's they're not bad. They're almost exactly the same as the force calculations. There's a couple of little tricks and pieces that you have to kind of include as you're applying it, but at the end of the day, it's all basic statics. So now when you go and you take your fluid mechanics class, okay, or fluid dynamics, you'll be able to do stuff that's in the first or second chapter right off the bat because you understand the basics of the statics, and that's where we're at, okay? Again, the water's not moving, the water is static, our wall is considered rigid. We can play the game. We can do what Sir Isaac Newton told us, right? Okay, they knighted the guy for a reason. So anyway, I hope that's made sense to you. If you've got any questions, leave us some feedback down below and in our comments below, and I'll be happy to try to resolve any issues that you have. And otherwise, if you found the video useful, please toss us a like on that, and be sure to subscribe to the channel, and we'll have a whole bunch more videos coming after this eventually. So have a great evening. Happy engineering.